Hey, welcome in. Well, we have a wild Gobi Scout in the chat. That is a rare and pleasant surprise. Oh, there we go. Let's get some. So sorry, just as I was about to start the stream, Streamlabs decided to. Sorry, OBS decided to log out of Google completely, which is very helpful. So I'm just trying to get everything logged back in at the moment. Oh, sorry. I was also wolfing down my lunch before we started. How's it going, Gobi? We don't normally see you in these streams, but here we go. Are you going to what? Yes. Okay. We have we have everything working. We have everything working. I hope. So so yeah, slight detour this stream from the usual thing. We're not going to actually work on our game engine and game code itself, but I'm going to have a poke at the I'm just going to poke at some generation code instead and various algorithms. So what I've done is I've set up a what's called a Jupyter notebook. This is like we're going to be departing from our usual Lua code and looking at this in Python because that's the language that the Jupyter notebooks use. But it will allow us to quickly sort of poke at these algorithms and then see how they result in real time. So, and I'm hoping this will also sort of stand up as a bit of documentation as well, so I can throw this up on my line. And so much of this stuff is sort of a bunch of broken links on the internet now that it's kind of hard to actually pull it together. So yeah, we've got this. I did a little bit of boilerplate work yesterday to get this going. So we've got a few Python libraries that we're using, which are not too important to look at in depth. We've got a function here called render that takes a map and then draws it out, and then this is we just make sure that there's walls all the way around the outside and that we strip off all of the boring graphing stuff because the library we're using to render this is normally used for graphs, but graphs are boring. We're going to use it for some maps instead. A few constants we're going to be working with, so we can reuse these values. So we're going to have a width and a height for our maps of 200 by 200. And then some values for our tiles. So we're going to say a air floor tile is a 1. Anything that is 0 is a wall. And yeah, and then a lot of this is going to be using randomness, and for random things you generally need a seed. And that seed is used to prime the random number generator, which makes it less random in theory, in reality, but it means that we can actually get predictable results. So we'll be able to get a constant value out of our functions with the same seed. And this is here just so that if we want to, we can swap this out for a fixed number in the future. And yeah, so I did some really basic map gen stuff off camera. And first one was well, just look at this. We basically create an array of width and height, and we set all of the tiles to wall. Oh, this is very tiny. Sorry, I'm sorry about that. Here we go. We set all of the tiles to wall. Is that too? Let me. There we go. Yeah, that's a bit. That's a little bit too big now. Okay, I think that's a possibly readable size. But yeah, so for this one we just loop over each tile, and depending on this ratio, if the value is under that, then we set. If the value we generate a random number between 1 and 0, and if the number that we generate is less than the ratio, then we set it to air, and that gives us a really, really terrible map. So this is this is effectively just noise. So this would be of no use to us in order to play, but we can tweak it. If we set it to 25% of the tiles, so maybe zoomed in a little bit too much there. Yeah, so if we set it to 25% of the tiles, we get more walls. If we set it to 75% of the tiles, we get a lot more open space. But generally, something like this is not very useful. It makes a good starting point though. So this is about as simple as we can get with it. The next one that I did off camera was another simple one, which was so while we have just pure randomness here, with no sort of uniformity to it, in this version we use something called simplex noise. Simplex noise is a extension of something called Perlin noise, and both created by the same guy. And Perlin noise was like the original version of gradient noise, which means that instead of being all over the place with the values are sort of more smooth. They transition, they transition into each other. So with this, we're doing a similar thing, but this will generate a value between -1 and 1, and if the value is greater than 0, then we set the tile to air, and this we can scale in and out, and that gives us a smoother look. So we can get a nice. This sort of actually even almost looks like a cave. You can sort of, if you imagined this as a thing, as an actual dungeon, this would look kind of like an actual sort of organic sort of cave, but you get these sort of disjointed areas where things aren't connected and things. But this sort of gradient noise is the base of a lot of world generation. So if you look at something like Minecraft, for instance, all of the biomes and things are effectively placed via interpreting Perlin or simplex noise. So it's like it's the standard for a lot of this sort of work. But if we instead set this directly to the value, we can have a run it again. We can see that we should get okay. That one has rendered all zeros. So this should actually return. Sorry, so that will. This is actually getting rounded as it stands, so I think it needs to. Yeah, so I'm just going to get it to output the actual values. Here we go. So yeah, so we what we actually get is this sort of gradient of values that sort of flow into each other. So rather than going from one harsh value, such as an air top, such as a 1 to a 0 to a 1 to a 0 and so on, like we were getting with the random, just a random choice per tile. The values here get a nice flow between them. And normally this is used to determine, so one of the examples that you'll find this used in is it will be used to create terrain. So by taking something like this, you can effectively say that the zeros are, the 0 point is sea level, and then effectively all of the darker colors would become water, the lighter colors would become land, and the really bright white would be like hills or mountains. And you can get sort of a nice organic sort of overworld map from it. What we're doing instead is we are clamping the value so that it's 0, 0, 1, and that gives us a sort of that gives us our sort of cave like structure. But yeah, so that's some really basic versions, but neither of these are actually any good in and of themselves. So we couldn't sort of generate these and then drop a player on this map and have them navigate it, right? There's too many sort of bits where they can't actually reach. If we created this and then spawned a entrance here, then the player would be stuck. So they're not on their own. They're not quite useful. So beyond that, there's a few other algorithms that we can look at. So one of these is my all-time favorite name for an algorithm, and that is the drunkard's walk. Yeah. So a drunkard's walk functions different to these other two. Actually, there's also another middle ground that we could choose as an extension to this one. So this is placing it. This is basically a random choice for each tile. So we actually get a slightly better result with instead of a random choice per tile, we can go for a random placement. So let's add a code block here. If we, we'll try and keep the actually, in theory, no. This is not gonna. I was gonna say we could, instead of randomly setting the tiles, we can set the tiles. So this will generate a similar effect, but what we'll get instead is we will randomly carve out parts of the map. So in this case, while we want a total will be the width times the height. And so while yeah, while replaced while replaced divided by the total is less than the ratio, we will do a x is equal to the yeah, this is what we're after. So while the well, we'll get a random x and y between 1 and the height and the width minus 2. This will give us a random point anywhere from anywhere within our map, but we'll make sure we don't target the first tile on any of the edges, so that we'll still have a continuous wall around. And then we'll continue to replace tiles until yeah, and if the tile is a wall, we'll replace it with air, and then we increment our number of replaced tiles. And then when the replaced tiles divided by the total is greater than the ratio, then we'll stop looping and we'll get our result. So this is so this is another way to get a similar approach. So we get a very similar result here, and every time we run this, we'll get a different sort of value. But this is very similar to the one before. It's not that useful, but this is more akin to how we're going to approach our other generators. So while these ones were mostly about generating a value for each tile, our other generators are going to function more akin to this. So this now gives us a good template for the future. Okay, so a drunkard's walk. So this will be generate drunkard. Generate drunkard. So this will work slightly different. So the way that a drunkard's walk works is that we're going to pick a tile at random. So we have x is equal to a random tile and y is equal to another random value. Actually, let's start in the middle. So we're going to start in the middle of our map. And what we're going to do is effectively, we're going to spawn a drunkard. And they are going to wander around this map and replace any wall tiles they bump into are going to get replaced with air. So we're going to give the so we will give the drunkard a let's give him 100 steps each time. Right, so then what we will do is we're going to set, as I said, we're going to set the tile we're on to air. So actually we should do, we should set the tile to air if it's a wall, and then we'll increase the number of replaced tiles. And then we're going to pick a direction for it to go. So effectively we're going to roll a 4-sided dice. And the direction will be a random number between 0 and 3. No, I do not want a if. We're going to match that direction. And yeah, that looks correct. So if we roll a 0, we're going to move one tile to the right. If we roll a 1, we're going to move one tile to the left. If we roll a 2, we're going to move one tile down. Or if we roll a 3, we're going to move one tile up. And then we will constrain these. So, okay, yep. So this will make sure that the x value is never going to be less than 1 or greater than the width minus 2. So therefore, similar to before, we're going to stay within our little box. And we're going to have an edge of walls around the whole map that we are not going to go into. And then, yeah, we're going to then decrease the number of steps by 1. And then if the steps run out, we're going to go back to the center and we're going to start over. Actually, if we put that at the top here, then we don't have to duplicate that logic, and steps can just be 0 for now. Yeah, here we go. So so we're going to set this up. That if steps is 0, then we spawn a brand new drunkard, and our current one. So effectively, each time we're going to have a drunkard spring to life. He's going to stagger around for about 100 steps. We should probably actually make that constant. actually, sorry, I'm being indecisive again. Yeah, let's put this at the bottom because it's it's a bit less. It's a bit more repeating itself, but it's what we mostly want from this is for it to be clear and understandable, right? Okay. So yeah, so we have max steps of 100. So all of our drunks are going to be able to stagger 100 steps before they pass out. And they're all going to start in the middle of our map. And while we have not hit the ratio of replaced tiles, if the tile the drunk is currently stood on is a wall, we're going to replace it with air, and we're going to increase the number of replaced tiles. And then we're going to pick a random direction in one of the cardinal directions, so north, south, east, and west. We're going to move one tile in that direction. We're going to constrain it so we don't wander off the side of the map. And we're going to decrease the number of steps each time. Once we hit 0 steps, the drunk is going to pass out and we're going to spawn a new drunk in the middle again. So now if we run this, theory, if we've done things correctly, actually, let's render the map at each step as well. So after each drunk, we'll get a new image. Oh. Okay, so I think our drunk is potentially not wandering far enough. Is our problem? Oh. Let's try this again. Okay. Interesting. Let's stop this and we'll instead instead we will so the walk is not actually carving out enough space, I think. So let's start with a very small amount first. We'll go for 1% of the map. Oh. Okay, so our drunk has gone for his wander and it's carved out a chunk. And we can see each progressive drunk has carved out more of the map. And this is giving us a nice sort of more organic feel. So we can, so if we increment that now, 10%, let's see what we get. Each individual drunk isn't contributing much though. Okay. So I think our max steps is still too low. Let's give them 1,000 instead. Okay, this looks a bit more promising. So yeah, so each time we spawn a drunk, they head off in different directions, and we get these sort of nice. These look these look very much like organic caves, right? So we have, yeah, seeing them evolve throughout the process is quite cool as well. So we can see that, yeah, and this is not quite a nice sort of organic cave shape. It's a bit rough around the edges in places, but one of the benefits we have here though is we know that anywhere we pick on this map is going to be accessible from anywhere else, because the drunks have actually been carving it out from that middle. So we get an interesting sort of structure. If we play around a bit more, we should be able to, if we increase the number of steps again, let's give each drunk 10,000 steps. And then we should be able to actually, well, at this point we should actually get less drunks drawing things out, and we should get more meandering. So that's, so these are actually, this is an interesting structure. So we see the sort of routes that they've gone out across. Okay, let's. So I think actually we should probably take the max steps as a parameter here. We'll replace that. That becomes max steps, and this becomes max steps. So now if we go for something a bit bigger, let's go for 25% of the map. Okay, so this is giving us quite a nice sort of cave structure, right? It does seem to be a bit biased towards the middle, though. So, because I guess they're all starting in the same place and they're all wandering around, we sort of carve out a big chunk in the middle, but then we get these little, the longer we set max, when we increase max steps, we tend to get more meandering sort of paths. So yeah, if we can set that to 50% of the map again. We actually get some quite interesting results from this. We probably don't need each of the steps to render now that we've figured out what we're doing and we've got it working. But yeah, each time we run, we get a different map. Yeah, I feel like 50% is probably a bit too much for this. So we probably want a lower ratio. Approximately a third even. Oh. I feel with a lot of this stuff as well, it's more art and feeling than science, right? So we can't really get a formula to tell us what the right values are for this. Oh well. So that's because we've given the drunk a long step. We can actually see that this has all been carved out by just one. They've sort of started here, they've wandered around, they've staggered around here extensively, before then eventually making their way up this way. Another big sort of staggering, and then so maybe 10,000 is actually a bit too high. I mean, that's not a bad Let's see. Let's have a look and see if did we just get lucky on the first try. Do we have a shortcut key for running the cell? We do. Okay, so if I put that there, can I just get this to run over again? Over, yeah. Okay, so some of these are not too bad actually. These are some quite cave-like structures, I feel. And as we have the values here, so if we decrease the number, we get more. We should get more branches. So we're going to. Okay, yeah. So we get less meandering sort of paths this way. But because they're all sort of staggering in the same place, we get a large sort of, all of them, I think a common sort of pattern is a large sort of central, area. But no, this is but yeah, this is quite nice. We're getting, this is more what we're after, but we could probably do better. So this gives us a nice sort of cave feel. Oh, that is a nice structure. This one, isn't it? Might actually. No, I don't need to save them. I was tempted though, very tempted. Yeah, we can let's. What if we increment the size a little bit more here? No. Or actually, what if we go down? What if we go down to 25% of the map? Okay, so these are actually. Oh, these are nice. So we're still getting a few sort of random trails. And yeah, if we go to the extreme and lower it right down, we're going to get basically just blobs. But if you were creating sort of a boss area map, I guess, something like this is not a bad. It's not a bad sort of bad place to start. So if you were to have a boss floor, we could actually put the boss in somewhere central in this map, drop the player close to it, and we've got a large sort of area for them to duke it out. But I think the slightly more meandering ones are definitely my favourite though. So yeah, so if you then ran an algorithm to find the furthest 2 points in the map, you could drop an entrance and exit way. You probably end up with like an entrance over here and exit somewhere over here. And that's a good sort of path to be fighting through, I think. Okay, so so with that, mind, the only downside of this though is you get very narrow corridors. So I may let's give it our drunk size. So at the moment he's 1 tile, but maybe this guy's drunk quite a bit. Couldn't resist the drunken munchies and is actually a lot bigger. So so with that in mind, we are going to we want half size. Yeah. Right, so we're going to want the size -1 divided by 2. I mean, it's probably not the best. Well, this will sort of work. It won't be very good for even numbers, basically. But instead of setting the wall tile, what we'll do is for yeah, we're going to loop over each of the edges. Okay, so we're gonna go out. Oh. We're gonna go we're gonna go from minus the edge size to the edge in each direction, and that will give us a delta, and then we want let's go for nx. The new x is x plus dx, and the new y is that. And for each of those, if nx is less than it's less than 1, or no, we want plus 2. Then we're going to continue so that we don't try and set any tiles outside of our map, and then we're going to set NYX to air. So this means that we should actually be able to draw with a slightly thicker brush now. So we will set the size by default to 1. And then if we run this again, we should get the same results. As we've been getting. But now we should be able to go size is equal to 3. And run it again. Yeah, now we get far more chunky paths. Alright. That's I think I like, yeah, I think I like this. What if we crank it? What if we go for 5? Right, yeah, so we get far more sort of blocky, wider corridors this way. I think 5 is too big. I guess it will depend on the size of the map ultimately and the and the size of the map and the style of the tiles and all of that sort of jazz in the end. But yeah, 3 is not a bad value. Let's see how badly it does if we set it to 2. If we set it to 2, yeah, it sort of chokes a bit because it's going to round down to 0. Okay. So this is so this one's so this is another good base for our maps. I think we need a bit more coverage if we're going to go for a chunkier chunky boy drunk. All right, so this is our drunkard walk. So we basically take a full map of walls and a random number generator seeded with our seed, and while the map has not been populated, so we get the total number of tiles in the map. We keep a total of how many tiles we've replaced. Then, while the given a X and Y, so then we start in the middle, we carve out up to max steps of tiles, given a brush of either one tile or multiple or sort of any other odd number of tiles, and then we'll set all of the tiles for the brush to air, and increment our replace count for any that were originally walls. We then pick a random direction, we move in that direction, and we decrement the amount of steps we have left, and if we run out of steps, then we spawn a new drunk in the middle. I feel like, and yeah, this is giving us similar sort of random sort of edges as we got with the Perlin functions, but unlike this one has we get a far more cavernous area in the middle, and we get a guarantee that everywhere is accessible. Though I do think I think the more meandering ones are a bit better. I think. Let's go for 25% of the map, and we'll let the guy wander. I'm going to try and find some values that give us a nice sort of more find some values that give us more spread out tunnels. I mean, it's not too bad. I think the ones we've got here. Okay, so that's a drunkard's walk. Another classic is cellular. Oh, the AI. It's almost like the AI is listening. But yeah, this is another standard one is cellular autonomous. So the most famous example of cellular autonomous is Conway's Game of Life. So with this, we effectively we populate a map, and then we set up a bunch of rules. So let's take something a bit more similar to what we're going to do. So this is generate cellular automata. Okay, so with this, what we're actually going to do is we're going to take a input map. So how cellular automata works is by setting a random percentage of the map to air. We'll then apply some rules that will then sort of expand or contract the existing walls and sort of smooth out the noise into something that matches what we are after. So we'll take the scale. So we don't need randomness for this one, actually. Okay, so instead of generating the base map here, we're going to take one in as a parameter, and then we will for each round copy the result. We're gonna make a, oh no, that's not base, is it? We're going to take a copy of what's currently there, and then for each for y in that range, go away. Okay. Yeah, so we're going to loop over each of the pixels, and we're going to have a count equals 0, and then for dx in the range of -1 to 2, for dy in the range of -1 to 2, so delta of the x and delta of the y, we're going to go 1 either side, and we're going to look at, basically we're going to look at the neighbors of the cell we're in. So go new x is equal to that, new y is equal to that. If new x is less than zero, or new x is greater than equal to width -1, or the same for the height, then we're going to increase the count, and then also, and the final one is, or if the current cell is a wall. So let's go over that temporarily. So we're going to effectively look at the positions. If it is less than or equal to 0, so if it's the first row, if it's the, or if it's the neighboring row, sorry, if it's the first row or the last row, sorry, it's the first column or the last column, or if it's the first row or the last row, then we're going to consider anything outside of our box as a wall. Actually, it should be less than, yeah. So anything outside of our map is considered a wall. And then we'll count that as a wall. And then if the actual cell itself is a wall, we'll also count that as a wall. And we're going to get the number of walls for the area. Then then we're going to want a couple more extra parameters here. We're going to want a spawn rate. So we can set that to 3 initially, and actually birth makes more sense. So we can if and okay, so these are two parameters. So each item in our map, if we look at one of our previous examples, look at this. So for every every square, it's going to look at the neighboring tiles. For each tile, it's going to look at neighboring tiles, and if there's more than a certain number of tiles, then we will effectively decide that there are too many, and we will sort of suffocate the tile and replace it with a wall. But if there's not many walls around, then we will replace it with a floor. So that's what this these birth and starve values are for. So so we've counted all the surrounding tiles, and now we have a count set. So then if count is greater than starve and the result is and the result is an air tile. Then we're going to set that to a wall tile, and we will decrease. We need the count. So total is. Oh no, we're just running we're just doing some rounds on this, aren't we? So yeah, so we don't actually need to do that check at all. So yeah, so if the count is greater than starve, then it becomes a wall. Else, if the count is less than birth, it becomes an air tile. I think that's it. Yeah, so there's a lot of looping here. So for each round we're going to take a copy of the current result so that we operate on this copy in our checks and any of the changes we make won't affect it, the next tile. And then we're going to look at each tile in that map. We're going to calculate the number of neighbors it has that are walls. We should probably we can add this as a I was going to say we could add it as a function, but we'll if we need it again in another method, we'll extract this out into a function. Actually, no, I will actually turn it into a separate function. So we want neighbor count. Def neighbor count. The data is okay. Yeah. yeah, so we got there we go. So this will calculate the number of neighbors for a given point in a map. So we're going to look at each tile in the 3x3 grid, and we're going to count them up centered around the tile that we're on, and we're going to count the number of walls. And if it's not on the map, then it doesn't count. We're going to take we're going to make this a tiny bit more generic as well. Okay, so count is now neighbors 4. There we go. That's a little bit more understandable now. So then if we run this, and we want to go, so instead of passing in one of our other our seed, we will generate random. So we go for 50% wall, and we're going to go with something that's random, and then we will set the what did we say for the defaults? Let's go with 3 and 5, which we picked mostly at random, but then if we run our code through this, we can see that it gets smoothed out. So I think maybe our values aren't quite correct here. So this was our input, and our output, it clumps together and it gets more into a shape. What if we move these values around a little bit? Okay, so let's give us some far more cavernous sort of feel. I would have expected more of a ball around the edge, though. So see if we decrease the amount of so this is giving us a okay, and then if we put this back to 3 and 6, maybe 3 and 6 for the values there. Okay, so we've got more of a sort of spread out look here. What if we go the other way to 0.6? bring down the star value. Oh, okay, we're sort of getting somewhere here. But yeah, this this function sort of smooths out the values. What if we actually go with the simplex noise instead of generate simplex, get seed, and a scale of 0.1. Okay, so it doesn't really, it sort of changes that slightly, but it doesn't change it dramatically. If we leave the scale at 1 though, we should get a different, very different structure. Okay, and then so a lot of this is just a lot of the generation is just fiddling with values until you get something you like. So this is actually not a bad look. What if we actually increase the number of rounds we do on the random? Oh, sorry, style was set far too low there. Still too low. I mean, some of these aren't too bad, they're just not values just aren't quite where I hoped they would be. I think let's increase the birth rate of the new cells. That sort of pushes things out more. So yeah, this is so a lot of this is a bit dark arty. Okay, what if we where we set this low? Oh, actually, now we're cooking. That's not bad. Maybe we need more rounds though. What have we got for 20? Okay. Yeah, this is now starting to look. So this is giving us a very similar feel to the Perlin noise now. Sorry, to the simplex noise. So just at a smaller scale. Although this one is actually zoomed in quite a bit. So if we were to if we set the scale on this one out, we get a very similar result. Though we do get a bunch more caverns, and it's a bit less, bit more random, I think, in this version. If we set both of these the same, what happens? Yes, that's less interesting. If we move the starve up, start with a bit more of the let's try somewhere in the middle. Okay, because these values don't overlap either, so okay, I think 4 and 5 worked good before, didn't it? Okay. It's slightly weird. I'm not getting the sort of results you would expect. So when you look at let's call up the browser. Okay, so here we go. So when you look at the generation by that I've seen in others, yeah, we're not getting the same. So I'm guessing the values I have are not quite tweaked correctly. Yeah, the results I'm seeing in other implementation. I've seen from like examples from others. They tend to have more of a sort of blotch look to them. Okay, so well, let's go back to this. So yes, we have about 45% of our 55% of our map should be air. So we have a definite bias towards air. Is the ratio going the right way there? Yeah, that's a lot more darker. So give a slight bias towards the air. So we want to, all right, let's try some different values. So we want, there's at least 5 of the 5 walls. We starve it. And all right, that's starting to look more like what we were seeing elsewhere. So let's go for a few rounds. Okay, yeah, I think this is starting to look more like a cave. The trouble we have is it reaches out to the edge too much, I think. But it's an interesting place to start. We can map, potentially we could map other things onto that. Out of interest, I wonder, so we tried the purlin noise as a base. What if we did a drunkard's walk as our base? So we, okay, so this can be a bit blocky, but this smooths it out quite nicely. So if we go for shorter walks. Oh, that is actually quite nice. So the combination of so far I think the combination of drunkard walk and the cellular automata is currently winning. The only downside I think is that we could potentially lose our universal accessibility around the map if the rules for the cellular automata sort of close up any of the paths. But Yeah, this is actually pretty cool. So what if we go for a small value? Hey, we get some quite nice shapes, I think, out of this. Yeah, because this is a bit blotchy, but then when it gets smoothed out by the cellular autonomer, we get quite a nice sort of cave shape to it. If we go for 100, many drunks on many walks. Okay, so that's a bad bounce. It's now taking quite a while to generate. So 100 was too short of a walk. We go for 500. Okay, and if we set this quite high, but the ratio quite low, we should get something quite sprawly. Yeah, so these are some. Okay, so I think so far, actually, the drunkard walk and the cellular autonomer are giving us some quite nice sort of results when we combine them. So we get some interesting cave shapes. Okay. So we've looked at the cellular autonomer and the drunkard walk. There was one other, let me check my notes. There was one other algorithm I saw that looked kind of interesting in this camp, and then we're probably going to switch gears a bit. Sorry, just as usual, my notes are a complete mess. Where's the so the other one was diffusion limited aggregation, which is a specialization of the drunkard walk, from my understanding. So from my understanding, there's a few different ways of doing this. We can if we fill a level of a wall, we dig a seed, tile or block in the center, and then until it's sufficiently done, we spawn a sort of drunkard walker, but instead of converting the tiles they walk over, we wait until they intersect with another tile, and then we replace the tile they came from or they were heading into. So do until the level is considered sufficiently full. Choose a block either from a given set or using a function. Choose a location from which to begin the block's walk. Okay, let's have a poke at this, because if we can get a better drunkard Actually, let's come back to this one. Let's mix it up for now. So these have all been, what we've done so far have all been looking at the the map from a purely random standpoint, right? So instead of starting on any kind of sort of baseline, we've been just carving out parts of the map at random. I think actually for this one, let's yeah, so we're carving out parts of the map at random. So the other way to generate a dungeon is to place down some rooms and interconnect them. So this time, let's have a look at a simple dungeon. Algorithm. Oh. Here we go. So in this one, we're going to take a seed, and we're going to take a number of rooms. Go away. Okay. So we can take a number of rooms, and then we need a list to store our rooms. Room. We then let's say the rooms can be up to 20 20 by 20 per room. And for each of the rooms, we're going to generate a width, an X and a Y. We're going to append it to a list, but before we append it, if 5 is probably a good minimum size for a room, I guess. The map is only 200, so actually min width and min height, we'll put those in as variables. To max width +1, min height to max height +1. Yeah, so we're gonna generate a random width and a height and a random position within the space, and then we want to make sure that width we want X to be so if we consider X and Y to be our top corner, our top left corner of the rectangle that comprises our room, then we will want that to be greater than the X position plus the width of the other room, or if X plus the width is greater than the other rectangles. X position, or the same for Y for each of the other rooms in the room list. Then this is effectively what's called an AABB axis line bounding box intersection check. So what we're checking is that the corners of one box, one rectangle, do not overlap another rectangle, and that's quite easy to do in that's quite easy to do by just checking the no, I think I've got this backwards. Oh no, yeah, sorry. So yeah, so if the corner of our if we look at the two corners of our box, we've got the top corner and the bottom corner. Sorry, the top left and the bottom right corner. So if the top left corner is horizontally is either side of the box, or if vertically we're either side of it, then we know that we're not overlapping. Sorry, yeah, no, we were the other way around. So we're checking that none of the, so this will be true if if we're not overlapping. So if all of them are, if not all of them are not overlapping, then we skip adding that room. If we do, otherwise we add the thing to a list and we go for dx in range of x to x plus width. For dy, sorry, that'd be new x, and for new y, in range of y to y plus height, we're going to set the value to air. So then when we run, so then we should be able to display the thing, so render result. And then if we run this, oh, sorry, we didn't actually call it. If we run this with 10 rooms, we should see 10 rooms scattered around our map, which we've got here, but it's not particularly very useful at the moment because we can't get between them. We probably want a few more rooms than that though, so we've got 50. Okay, they're getting quite close though. Some of these are butting up against each other. So we want to make sure wait, I think I might have the intersection code wrong. Here we go. Let's so if we want to test the collision, I remember seeing there was a good description of the maths on MDN somewhere. No, that was the one we were just looking at. That is the, yeah, this is the form. Okay, so it's ands instead of ors that we're after. Okay, so it's close enough. I knew it was off though. Okay, there we go. So these are all now non-overlapping. If we start to crank it, we should still, okay, so there's no overlaps, but they can get right up close to each other. So we want to make sure there is a we want to make sure there is at least a 1 pixel gutter between them, so a 1 tile gutter. So yeah, so we have a wall between all of the we have a wall between each of the rooms now. And then we actually need to tunnel between them. So we could probably abstract a couple of these because they'll probably be useful in other things. So we want to with that we can then do actually no, we probably don't want, let's add something for carving out the room. So for each room, carve the room, and then we want to carve up a tunnel between these rooms. Yeah, so when we carve a room, we have an X and a Y, a width and a height. And when we carve a tunnel, we have 2 points, x1 and y1 and x2 and y2. And we probably want a size as well. Set that to 1 for now. We're going to want a direction as well. So we'll want we'll want to take the random. No, let's go with that. Okay, so then we'll pick a direction based on the largest difference. So if x1 x1 minus x2 is greater than y1 minus y2 else. Okay, so if the x direction is the longest direction, then what we'll do is for okay. Actually, I think we need to. Okay, so max x is okay. So we're going to want the minimum and maximum values. Okay, so for x in range min x to max x plus 1, we are going to set data so min y and x is equal to air. Sorry, I'm confusing myself more than I should be on this. So yeah, and then this way around we want to go from min y to max y, and we want to set y. So this will always carve out along and then up. So we still don't have anything there, but we can go if the room list is not empty, then we also want to get the center of the rectangle. So to get the center of the rectangle, we want the x, the y, the width, and the height, and we want to return we're going to return the half x plus half the width, x plus so we want to go from cx cy is equal to the center of this, x oy is equal to the room list, the last item in the room list, and we want the x and the actually -1, and we can just pass all of the values that come back from there, and then we want to draw a tunnel and result from we want to draw a tunnel from our room center to the center of the other room, and we want this side, the width of the tunnel to be 3. So we have this at the moment, it's ignoring the brush size. Oh. So for this, we would also want to take the size of the edge, and then for so it's the same as before, our code before, and then we can probably actually separate out this drawing. So we've used that a few times now, so let's actually abstract out that drawing with a brush. Okay. So we're going to want to draw. We're going to abstract out the drawing. So def data x, y, size, value. So okay, so this is our data, and then this is an integer, another integer, value is also an integer, and size is an integer, and we'll default it to 1. Okay, so given that, we'll take the width and the height. And we want to take the center. We want to get the the origin will be the x minus size, and the width will be that. So for the new x in the range of origin x to origin x plus size, if the value of new x is greater than 0 or less than equal to width, and the new x is greater than, yeah, so that makes sure we're safe to draw it on value. And then actually, I think we will flip this around a bit. So if it's outside the bounds, then we continue. Otherwise, we set the value. Okay, so if we go back to our previous implementations, the Drunkard Walk has one of these. So we can strip out, that is, okay, so we'll draw and we will return the number of things it replaces. So for this, if the value is equal to the value, then result increments by 1, and we'll return the result. So this will return the number of values it updates. Yeah, and then so for something like this, we would then just go Drunkard's Walk. For here we would go replaced, plus equals draw. There we go, and then that can go away. We don't actually use the direction after we use it, so we can embed that in there. Yeah, that's much simpler now. And then if we run it, we still we didn't run the cell up here, did we? Run that, then if we run this one, we get our drawn shapes. Let's set. Wait. This is run. It's only running one frame. So it did run quite a few times. That does not look like 20. It's replacing 25% of the screen though. Something funky is going on. Let's double check that the values make sense. Okay, so it's at 100, 100. It's drawing. Oh, hang on. I think I have the if statement flipped in here then. Oh, hang on. No, that should be value. There we go. So the first one returns 9, and there we go. Now we're getting back to where we should have been. So let's take our values, the debug info out of that one. Yeah, so this is now generating as it should have. So we're getting some interesting shapes, and our code is much simpler now. Cellular automata, this one. This one doesn't need a brush size. Okay, and then for this one we can draw for X, for Y. Yeah, for each one we will draw the here we are. So yeah, if we drop our draw method into those now, we should now get a, oh, it has no object shape. Carved tunnels. Result. Where is this going? Going wrong. So we carve a tunnel with data xy, find the middle, and then we draw pass the data in. Then, and it's passed from there. Why is this? Why? So this is getting called with a able to update this one. What is actually getting passed here then? So it's getting the array. for now, let's just draw one-way paths. So data. Oh, no, this is the wrong way around. Min, y, max. Min, y, and x there, and then this one should be max x and y. Now if we run it, what do we get? Okay, so that did not draw that has not drawn the paths as it should have. Something else is going weird here. Yeah. So those were the wrong way around to begin with, but we're still not getting it's still not drawing the tunnels. So it should be drawing from each room into the next room that was generated a line. Let's work with less values for now. Oh. Okay, so we've got it's generating the rooms, but it's not connecting the it's because it's drawing to itself. That's why. Okay. So that's sort of connecting them. Still not quite right though. The tunnel generation is slightly off. Here we go. Yeah, so okay, let's for x in a range of x1 to x2 plus 1, we're going to set to air for y in range y2 to there, we're going to set it to 1. So we want to find, then we want the step. . . . . . . yeah, then we want this step to match the direction. Yes, that's now drawing. Drawing corridors between places. But oh, it is broken there. Okay, so it's ever so slightly broken on the God, this should not be as complicated as I'm finding it. My brain is definitely not working at the moment. The streamer brain is strong today. Ah, hang on. So a little a drink would probably help. So, so we want to connect. We want to carve a tunnel from one room to the next. We've got the center point of each. So we want to draw a horizontal column corridor. From one to the next, from our current room to the next one. So alright, so we want to go from the smallest x to the largest x. That's the largest x plus 1. And then we want to go data. Y1 x is equal to air. Then for data, for y in a range of min to max, we want to do that. Yeah, that should. And then obviously we get two rooms next to each other. Okay, so that seems to be connecting things. Yeah, so this, okay, these are connecting. It generates less interesting things, this, because the corridors tend to overlap. But I think this is as simple as a room generated dungeon can get. He says after all of the struggling so far. So let's try this with the let's try this with our draw method. And here we go. Yeah, now we get. I was going to say we get nice fat corridors, but we are missing one now. Did I mess that up when I... No. X, Y value size. Go to the definition. I am drawing it the wrong way around. Yes, and then this is the wrong way around as well. And then, yes, okay, so this one's now generating properly again. And then if we try our simple dungeon, here we go. We've got now got a box-based dungeon. So let's go. Let's go 10. Let's see what we get here. Yeah, so this is the simplest version of a generator for basic sort of traditional dungeons where it's sort of a enclosed network of corridors and things. It's not the best though, because what we end up with is because we're just mapping each room to the previous one, they tend to overlap. The corridors and stuff tend to overlap. So one way we can work around that would be to draw the corridors after the fact, by instead finding the closest rooms and mapping that way. But we'll save that one for... We'll leave this as its most basic version though. We will... we should add... let's abstract this as well. So we've got the draw. We've got our draw method. We're also gonna let's add a draw rect on here as well. So draw rect, and we'll put value in. Yeah, so we're going to need that one again very soon. So we'll take that out, and instead we will draw a room of air. So draw a rect of air, and yeah, we still get okay because okay, so the next interesting one in this, in terms of room-based map generation, is something called binary space partitioning. So instead, whereas in this one we just randomly place the rooms, in binary space partitioning, I'm getting quite scared as soon as I mention a thing. The autocomplete is actually entering it. So I guess that shows we're on the right path, right? If even the LLMs are able to predict our next area for investigation, then we're not doing anything too out of the sensible. Okay, so I think we will go for the same. We'll go for the same sort of input of number of rooms, and then we'll have the min, max, width and height, but what we do instead with this is, instead of, okay, so we take our result set, but we take the the size of our game map, and then we create a rectangle around it. And then what we keep doing is we keep cutting that rectangle in half. We pick a rectangle at random if it is big enough to be split into 2 rooms, then we do so, and we keep doing that until we get something that is, we have a structure of the different rooms. So let's so if we go back to Rogue Basin, the idea is we keep dividing each area. So we choose a horizontal. We choose a random direction, horizontal or vertical, and a random position, and then we split things in half. And then we take the next one and we do the same again. We keep splitting and then we end up with a nice sort of disjointed shape. So I guess we want rounds rather than rooms. So if we say we'll go for 5 rounds. X, Y, width, height, and we're going to have X, Y, width, and height. We're going to return two widths and heights. So we go match. Oh. Case 0, we will go horizontal. Pick a split and we'll return 2 splits. And then for the other one, we'll do the same with the height. Actually, this is probably a bit more readable if we go something like this, I think. Yeah. Okay, so we're going to split the rectangles. Okay, so we want a random number generator, and then for each round we will go new X, and then for alright, this I'm not sure on. So we're gonna end up with rectangles that are too small to be a room. Potentially. So if we're going to get, so we kind of want to constrain it. what we could do is actually, instead of, oh, sorry, I still have the browser open. Sorry. So, I really need to stop doing that. So we're going to need to split the rectangle. So following on, we can split it randomly. We can roll a dice, a two-sided dice, well, I guess flip a coin. Flip a coin, if it comes up heads, effectively, then we split it horizontally by picking a random point along the width. And if it comes up tails, we split it vertically at some point along the height. But that's not necessarily what we're after though. So I think instead we'll go for, instead of returning 2, we will return a list of split rooms. So let's take this as a parameter instead, and we won't return anything. And we will generate our spot. No, this works. But what we need is min width and min height. Okay, so we need to pass those 2 through. And then when we split it, we split from min width to the width minus minus min width minus 1. So that will split it there, and the same with this one. We want to go min height. Height minus min height -1. So now we're going to split. We're going to split in a way that means we have a room-sized space on either side. And then we will so we're going to split so we have a room-sized space on each side. And so for each round we will go through each rectangle, and if we can't subdivide anymore, we will continue. If we can't subdivide, we'll continue, and then and part of this is randomly that, and the width is greater than twice the min width. Okay, so now we're going to divide down into rectangles for each round. And now create our rectangles. Then for each of these rectangles, so we're going to go from the min width to the size of the window, and the same for the height. Get the center point, and then we will go new x is equal to the center x minus half the width, and the same for the height. So actually we can still do this with rooms. So we want to draw 5 rooms, then the number of rounds is so it's because we double the size each time. So we've got power of 2, so we go around No, we'll go, I think, yeah, I'll leave it as rounds. So we'll have a room list again, like in our previous example, and in this we'll go room list append, and then we'll draw that, we will carve that out. And then yeah, so if this is, if we can't divide, then in our new, we'll have to append the current rectangle back to the list. So then we get our rooms, and then for and then we want to do the same tunneling as we did before. So okay, just making sure it's all. We have the center point, so we just need the other room center point, and then we can draw the tunnel. Then when we run this, here we go. So now we get a more interesting dungeon. Oh. Split rect. Okay, so when it's getting very narrow, this is failing. I don't think we need to go one less in those. Should, no, still getting. Okay. Yes, this ends up smaller than it can cope with. So you shouldn't actually be able to get there though, because we say if the width is less than twice the min height. Hang on, I think I I had the subtract 1 on the wrong side. What are we getting now? So yeah, so this should be if we win the coin toss, or sorry, yeah, here is the problem, isn't it? Or the height is less than 2 times the minimum height, because we want to force it into that split if the other one is not available. Width. If the width is greater than or equal to 2 times the two times the min width, there we go, that should be more stable now. So So I think the max room sizes are getting in the way here. So I think, what if we take out the max? And then see what do we generate then? Missing comma. Okay, so these are not correct either. So we are creating the rooms, and we create the new rectangles. We have our room list, and then we create each rectangle. Sorry. For now, let's set these to the width and the height. -1 on each. Or actually, it's -2 on each. So then we get a room that is interiors. This looks a lot more like the inside of a place. I think. Well, it's been 3 hours now, so I think we'll mark this one as incomplete. And I'm going to call it for today. I think we'll carry on with some more of these, some more of this next week. But so far we've mostly been looking at some high level stuff. So we have basically the ability to create a random map using either random tile selection, flipping a coin for each tile, basically randomly placing tiles until we get the right ratio, or by using simplex noise. We have a method for carving out a area using the drunkard walk algorithm, which gives us these nice sort of cavernous looks. We also can use cellular automata to smooth out an existing map. It gives us some nice cave-like shapes, and we can also apply these for other dungeons. This method to other dungeons. We can randomly create rooms and then interconnect them. This is for more of a room-based style. And I think all of these are, as I said, are very low-level sort of randomizations. What I think we'll end up with more as we progress will be a sort of hybrid between a room based and something like the where we select the location similar to the room based, and then we use something like a drunkard walk or cellular or cellular automata. Sorry, words. Yeah. To create sort of more random sort of shapes, and then maybe we'll adapt the corridoring techniques to give us some more sensible corridors. We can also use things like Delaney triangulation and things to find the closest rooms and make sure that we're connecting rooms to their closest neighbors, and things. So there's still a bunch more for us to do, but I think as I said, the end result will be a combination of different techniques pulled from each. And I think when we actually do implement this in the game, what we'll end up doing is having a mix and a match of different generation styles for different themes. So we can have this is currently an accident, but this would make an interesting sort of if we wanted to have a map that was sort of based as, I don't know, some sort of castle or something. If we had tiles for castle interior, then this sort of generation would give us a good place to start on that. So we might actually have to come back to this at some point. I'm hoping to get it back to being able to have the small rooms in one in each box, but yeah, basically just better distribution, randomly distributing like this, and better tunneling with like a drunkard's walk for each room, then tidying that up with the cellular autonoma. We'll get we can probably get some really interesting shapes by layering on these various techniques. So I think next week we'll continue with that and see how far we get with and hopefully we can move through some of the fancier sort of approaches, and hopefully we can also look at some maze algorithms, because those are also quite an interesting way of doing it. And at a later date, when we have the Delaney triangulation of the various rooms, and they're randomly spread out, we can then apply some of the maze algorithms to generate ourselves interesting routes through the rooms. And as I said, those rooms can then be carved out using the drunkard's walk, and then maybe we come up with tunneling that is a bit more meandering rather than the straight lined approach we've here, the very naive straight lined approach we have here. And we're going to get some really interesting shapes at the end of it. And then once we've got some interesting generation that we think is useful, we can then take that back to our game, and we can start to implement that in the engine. But for now, I think I'm going to call the stream. We should be back next week, and I will be back on I'll be back for some gaming on Wednesday. If this sort of thing interests you, then please, there is a link to Discord in the video description. Do join and come and chat about all things procedural generation, because I find this whole area of things really interesting, like the way in which we can just create something out of nothing just by throwing these algorithms at the problem, and then the interesting solutions, the interesting sort of things we're going to find when we start to layer them up as well, and the interesting things we're going to be able to generate is going to be really interesting. So yeah, I'm going to call it for today. If you've liked the video, give it a like. If you would like to see more, then do give the channel a sub, and I will see you next time. Bye.